Welcome to Algebraic Topology. This is going to be the first lecture. And before we get started with the material, maybe we should begin by saying what algebraic topology is about. Now, notice there's the emphasis on the word algebraic. So it has something with history. So a long time ago, maybe in like the 1880s to 1900s, mathematicians were interested in point set topology, which is a way of working with spaces without emphasizing distance or size or anything like that. So a lot of the definitions that we use nowadays, such as connectedness, compactness, all that, open sets, all that stuff, that is the Hausdorff property, all of that stuff originated around in that time period, actually a little bit after that as well. Maybe I should not, maybe if we can like push it to maybe 1950s or something. It did not develop like all the way in the beginning of the 1800s, but this is where certain ideas began developing. And this is a type of topology where you're interested in set theoretic properties. And also around in this time period, Poincaré had a big influence on what became known as combinatorial topology. And combinatorial topology, and we will see what that is later in this course, this is where you work with these things called simplicial complexes. One can think of them as generalization of graphs. So it's very combinatorial in nature. A simplicial complex, it can be described as a finite amount of data that fit together in a certain way, and hence the name combinatorial topology. And these were pretty different from each other. In point set topology, you often considered rather bizarre spaces and things of that type, whereas in combinatorial topology, the spaces were quite nice. They were compact, they were connected, continuity was easy to understand. So all of the nice properties, the Hausdorff properties, all of the properties that we're used to, they were automatically true in combinatorial topology. And rather, one was interested in the problem of, one was interested in something called homology, which we will talk about in this course. And these two approaches to topology were very different. Point set topology, it's called point set topology because it feels very much like set theory. You're just using set operations, unions, intersections, mappings of one set, pull back, push forward of a set, subsets, choosing elements, and all of that. That's why it's called point set topology. And it was very different from another approach to topology, which is combinatorial topology, where you were not interested in any of those things, and you were interested in problems of homology and how to compute it and what it means and all of that sort of stuff. So because of that, we had a distinction between, you can say, the two different schools of topology. Now, in the 21st century, I think we can say that this is point set topology. I would say this is outdated as far as research. So it would be very hard to find a mathematician who does research in point set topology. Now, of course, it exists. People can do research in anything they want. I believe some people might even do research in classical Euclidean geometry. That is a thing, but that's not something that people typically work on anymore. The big problems in mathematics, none of them are from point set topology anymore. And the math community has this feeling that all of the general topological spaces that one comes across throughout the world of math has already been nicely described in the world of point set topology. So there's no need to really go any further. Generally, what research in point set topology often comes down to is working with unbelievably bizarre spaces and producing certain counterexamples and things like that, type of spaces that one never really comes across in other areas of math. So because of that, it became sort of outdated. But historically, the purpose of point set topology was to unify a lot of mathematics that one comes across. So you see something in analysis, or you see something in like analysis, let's say, or the kind of topology that one comes across when you're working with like manifolds and things like that. It was there to sort of unify those things together with a common language. So there was certainly a need for that. And combinatorial topology has improved. So this route, this improved into what is now known as algebraic topology. And I would say this is probably like the 1950s, 1960s. This is sort of where algebraic topology began to emerge, somewhere around in that time period. You see, combinatorial topology, it specifically worked with topological spaces that were known as simplicial complexes. And if you have a topological space, which is not a simplicial complex, then it was not really suitable. And mathematicians realized that you can generalize homology to spaces in general. And by doing so, it became known as algebraic topology. So it's sort of the same idea, but pushed even further and generalized to arbitrary spaces. And there is a lot of usage of algebra. You work often with commutative groups, but you also do other things. We're not going to do any hardcore amount of algebra here because we're trying to keep this class as self-contained as possible. But this is sort of why it's called algebraic topology. I think that we can probably maybe just call it topology, because that's usually what people mean. If you meet a mathematician who works in topology, it almost exclusively means that they're going to be using the kind of techniques that we talk about in this class. They're not working in point set topology. They know it, they're not working on it, and they're going to be using techniques of algebraic topology. And it's called algebraic topology because, as you will see, you often replace problems in topology by problems in algebra, and you reduce it back to algebra, and you work out the algebra, and it helps you say something about topological spaces. So that's just a little quick history lesson on why it's called algebraic topology. So like I said, I think maybe you can just call it topology. In some graduate schools, if you take a course in topology and they call it topology, they almost always mean it's a course in algebraic topology. They just call it topology. But for historical reasons, we'll just call it algebraic topology. Now let's, before we get into the lecture, let's perhaps say, what are the prerequisites? The prerequisites for this class. What do you need to know? So I would say the most important thing is you know something about writing proofs. You probably have taken, let's say, an intro algebra course. So that means you know what a group is, and you're also comfortable with these things called quotient groups, which is always part of an algebra course. So when you take an algebra course, you learn about groups, you learn about subgroups, and you probably recall learning something called cosets. That's what we call quotient, quotienting a group by a subgroup. Those are the cosets. As normal subgroup, though not as important in this class. Actually, abelian groups will be sufficient for the most part. So when you take an algebra course, you'll learn a little bit about proofs, so you're comfortable with what a group is. You do not need to know anything outrageous about groups, but you are comfortable with them. Like, you know what they are, you know some basic properties, and you can do some basic proofs involving groups, and you're comfortable with working with quotients. So like, you have a group, you quotient out by another group, you're comfortable working with that object. So you have like an intro to algebra course, and maybe you've like taken something like advanced calculus. You have a background in advanced calculus. Advanced calculus is not really used in this class, but some of the topological ideas are part of advanced calculus. So you have a little bit of exposure to that. But what's interesting is you do not really need to know any point set topology. So this is the part which is pretty impressive. Like, if you do not know what a topological space is, you can still probably succeed in this class, as funny as that sounds, because we're going to try to present this class in the most self-contained way that is possible. So what you can do is, so if you see the phrase, X is a topological space, you can just replace it by rather that X is some subset in Euclidean space. It's a subset. So I imagine you know what Euclidean space are. That's why I mean advanced calculus background. This is not a surprise for you. So these are vectors, n-dimensional vectors. So it's just a subset of n-dimensional vectors. In advanced calculus, you talk about what it means for something to be an open subset, a closed subset. probably seen that, so you have that background, so you're comfortable with that. Now, the point of a topological space is to free yourself and not necessarily assume that X is sitting inside some Euclidean space, but maybe in the beginning or for the time being, you can just assume that's what X is. If you're not sure what a topological space is, then this should be enough in most cases. And if you know what a metric space is, you can say more generally, you can assume X is a metric space. So it has some kind of metric on it, a distance function. So I imagine the people who are watching this probably know what a metric space is. It's a set with a metric function that evaluates distances between any 2 points in X. And when you have a metric space, then you talk about what it means to be an open subset, a closed subset, what it means to be a continuous map between metric spaces and things like that. So if that makes you feel better, you can just assume it's a metric space, because Euclidean space is a special type of metric space. If you have two vectors, you can find their distance by using the Euclidean distance or the Pythagorean theorem or something like that. That would be your distance function. Like the whole point of topology is to say that in topology, we do not care about distances. And so the metric is a distraction from what we truly care about. That's why we try to do things in a more general sense. And that's the most general sense is the topological sense. But if you're not sure what a topological space is, you can just assume it's that. And that should be good enough for everything we do in the class, as surprising as that sounds. Hence, this is the reason why we say it's a course in algebraic topology, where we do not emphasize point set topology that much. And so I'll tell you what the topics for this course will be. Maybe before I get to the topics, I should say how to use this course. So this video will have an attached PDF document that will have homework problems. And the way this course is intended is you watch the lecture, and after you watch the lecture, you can then try doing some of the homework problems. And you can find those homework problems in the video description. Now, at the moment, while the videos are being uploaded, you will not find any documents. But once all of the videos have been completed, and once all of the homework has been typed out, then the video will be updated, and then you will find it. You will find all of the practice problems there. And that's the way you want to learn math. If you just watch the videos, that's not really good enough to learn it sufficiently well. You want to be able to practice your knowledge, and it's through practicing problems that's the way you end up learning this. Now, let's say what the textbook is. So the book I would recommend, it's called Topology and Geometry by Breton. And this is a graduate text in mathematics. Though the title is a little bit deceptive, because there's no geometry in the book as far as I know. It's only a book on topology. But everything that we're going to be doing this semester can be found in that book. Though the disclaimer, I would say it's a hard book. Okay, so just a warning, it's a hard book. So if you have read Moncrief's for point set topology and Moncrief's for the fundamental group, then Breton is a very big step up in difficulty. But hopefully these video lectures will help you follow along. So that's the recommended book for the class. And let's say what the semester plan is. So the goal of the course, so this is the goal of this course. There will be 3 main topics. So the first topic we're going to talk about is something called covering spaces. The second topic is we'll talk about homology. And the third topic is we'll talk about manifolds. And these will be specifically cohomology of manifolds by differential forms. So these will be the 3 main topics. Now, as indicated, the goal of this class is to be self-contained. So it would be helpful, so for part 1, it will be helpful, but not required, to know what is known as the fundamental group. The fundamental group of a topological space. If you know what that is, at least a little bit, maybe you're not an expert on the fundamental group, but you at least know what it is, then it would be helpful to understand the material and covering spaces. But it's not required. We're going to do it in a self-contained way. So perhaps you've seen what the fundamental group is, how to compute it. Maybe you've seen this thing called the Seifert-von Kampen theorem, which is the main theorem that you use to compute the fundamental group. But if you're not sure what that theorem is, or you're not sure how to use it, that would be okay. You actually do not need that. We will be using a different approach to the fundamental group through what are known as covering spaces. So this will be the 3 topics. We'll spend about a third of the semester on each of these 3. And I think this will give a nice, good overview of algebraic topology. All of these topics will use algebra. We're going to understand covering spaces through working with groups. Homology will use groups. Manifolds will use vector spaces, actually. This is why it nicely fits together with the theme of the course, where you're going to be reducing problems in topology, problems in algebra, and then the algebra will help you solve your problems. Now, because we want to keep this course as much of an introduction as possible, we will have to make some compromises. So we will compromise. So we will compromise and avoid getting into some of the technical proofs. We will have proofs, but if the proof is too technical, we might give a partial proof, or we might say what the issues are without getting into too much of the specifics, because otherwise it's going to take time away from the other topics, and it's going to make the course a lot more difficult. In fact, some of the more technical proofs involve better knowledge of algebra. So you have to be comfortable with category theory, with commutative algebra, with tensor products, with exact sequences, with derived functors. And we do not want to go in there, because that would make it not a very friendly course for an introduction. So we will have to stay away from that, but at least you will know the things that we stay away from, and then if you're interested, you can read about it yourself. The book by Bredin actually does get into those technical details, so that would be a place where you can find them. So we will have to avoid certain technical proofs, and we will also not be able to explore every topic as much as possible. So for instance, homology is something you can spend an entire semester on, in fact multiple semesters all on homology, but we're only going to spend like a third of the semester. We just want to be able to say what it is, how to compute it, how to use it in some cases, but we're not going to be able to say everything we want to say about it. So we will not be able to explore certain computational methods for computing homology, because we're going to have a lack of time, and also those other computational methods are going to be a little bit more involved, so it will be less friendly of a course. So that's like the overview of what this class is about. Now, what I want to talk about in the first lecture is I want to talk about this thing called homotopy. I would like to start with this. It's going to be very useful for us. I do want to, at some point, hopefully by next class, define what the fundamental group is, and that will require this notion of homotopy. So this is like a good way to start. So let's say what a homeomorphism is. Let X and Y be 2 topological spaces. And again, like I said, if you're not sure what a topological space is, then you can just pretend that X is some region sitting inside n-dimensional space, and Y is some region sitting in possibly a different dimension in m-dimensional space. And we say X and Y are homeomorphic, or you can even say isomorphic as topological spaces. if and only if we can find continuous maps f from x to y and from y to x, continuous maps, so that f and g are inverses. So f composed g, that would be the identity map on y, and g composed f, that would be the identity map on x. So that's what it means to be homeomorphic spaces. Perhaps, now you've probably seen homeomorphisms perhaps defined in a different way, like alternatively, you can say you have a function from y, a function from x to y, which is a bijection. It's continuous. And the inverse function from y to x is also continuous. You have to be a little bit careful. Just because the function is continuous, the inverse function is not necessarily continuous. The example that I always like to use is, imagine you take the interval, the open interval, from 0 to 2 pi, and then you take the circle, right? So this is going to be x, this is going to be y. X is a subset of the real line, and y is a subset of the real plane. And then you can define a function going from x to y, which is going to do this. F of a number, let's call it t, is going to be equal to cosine t sine t. So this is the way you typically parameterize a circle. And as you can see, the reason why we omit the right endpoint, because 0 and 2 pi become the same number at cosine at sine, because these are periodic functions. So they both get mapped to the same number. So 0 is being mapped to 1 comma 0. So they both are being mapped to this point 1 comma 0. So you have to exclude this endpoint, because otherwise you do not have a bijection. And this is a continuous map. This is a continuous map. But you go backwards, but the inverse map, so this is a bijection. F is continuous, and it's a bijection, but if you go backwards, if you go from y to x, this is not continuous. And you can see from the picture why it's not continuous, because the map, the inverse map that goes from y to x, notice what it's doing to 2 points. If you have a point that's on this side of 1, 0, and you have a point on that side of 1, 0, then this blue point is going to end up over here, and the red point is going to end up over there. So what's the problem? The problem is the blue point and the red point are close to each other, but their image under F inverse is far apart. So things that are close together get separated, so you're violating continuity. Intuitively, the way you go from the circle to the line is you have to take a pair of scissors and you have to cut it and you open it up. So you're destroying your space, right? You're tearing your space apart. That's not a continuous operation. So that's why we want the inverse function to also be continuous. Intuitively, when we say that x and y are homeomorphic, it means that there's a way to twist or deform one space into another space. Now you can see that it makes sense that no matter how you deform this circle, you can never turn it into that. The only way you can turn the circle, and you have to actually destroy it in order to open it up. So as you keep on moving that circle around and twisting it and doing whatever you want with the circle, you can never turn it into that line. So intuitively, that's what a homeomorphism is. It basically is trying to say that you have two regions that where one can be sort of twisted and reshaped into another region. And the requirement is that you have this kind of condition. Now, if you know what a topological space is, well, before I say anything, this is probably the way the definition was presented to you, that you have a continuous function between two spaces. It's a bijection, and the inverse of it is also continuous. But alternatively, you're saying this, because if the inverse is continuous, you can call that F inverse, that's continuous, and then the compositions will give you the identity mapping. So this is an alternative way to say this. So if you're familiar with topological spaces, then here's a way you can understand this. So here is how we can understand homeomorphisms in the language of topological spaces. So again, you do not need to know what a topological space is. If you happen to know what it is, maybe you'll appreciate this more, but if not, you can sort of ignore this. So a topological space is a set together with a topology. So this is a set, but a topological space also has something called a topology on X. And then we have another space Y, and we have a topology on this one. So maybe we call the T subscript X T subscript Y. So we have a set together with a topology. So when we're saying that there's a homeomorphism, when we're saying F is a homeomorphism, what we're saying is F establishes a bijection not only between X and Y, it also establishes a bijection between the topologies. So in what way? So F, as a map from X to Y, is a bijection. And if you give me something, if you give me an open set in Y, so by definition, an open subset of Y is something that belongs to the topology of Y, then because this is a continuous map, its inverse, if you pull that back, you get something in the topology of X. So if you have something that belongs to the topology of Y and you pull it back, then you get something in the topology of X. And furthermore, it also works the other way around. That if, you see, this right here is continuity. That's the topological definition of continuity. So if you have the pullback of an open set is an open set. So this will give you an open set in X. And furthermore, if you pick something in the topology of X, then f of v, the push forward, will give you something that's an open subset of Y. Now here you have to be a little bit careful, because in general, if you have a mapping between two topological spaces, it does not necessarily mean that open sets get pushed to open sets. However, because this is a homeomorphism, the inverse map from Y to X is continuous. And so if you pick an open subset in X, right, so V is an open subset of X, then it would mean that F inverse of V will therefore be an open subset of Y. But this is just another way of saying F of V. So this is where the homeomorphism assumption is being used. So notice what's happening here is F is not just a bijection between points in X and points in Y. F also establishes a bijection between the topology in X and the topology on Y. If you pick something in the topology of Y and you pull it back, you get something in the topology of X. And likewise, if you pick something in the topology of X and you push it forward, you again get something in the topology of Y. So F establishes a one-to-one correspondence. So this is what we're basically saying. So the idea here is a homeomorphism between two topological spaces establishes a one-to-one correspondence between points of X and Y and open subsets of X and Y. So it does two things for you automatically. And that's why we say it's the same, right? That's why we say that X and Y, so we say that X and Y are the same topological space, because there's this one-to-one correspondence. You want to think of a homeomorphism as some kind of dictionary. This is one language, this is another language, and you're converting something in one language to another language, and the conversion is a one-to-one correspondence. Anything that is an open subset in one is an open subset in the other, and the other way around. So you really are doing the exact same thing. It just is presented using perhaps different notation. That's why it's sort of like a dictionary between two languages. That's really what homeomorphism is. That's why we say X and Y are the same as far as topological spaces are concerned. So what is homotopy? So homotopy is a weaker requirement. And basically the idea is that x and y could be different as topological spaces. So they're not homeomorphic to each other, but maybe we can change x into y through a continuous process. So the idea of a homotopy is that sometimes you can have two topological spaces and they could be different, but nonetheless you can change one space into another space, and the process by which you change x to y is a continuous process. So to make this precise, we need some definitions. So this is sort of the intuition for what this is, and we'll give examples afterwards, and then you'll see what we mean. But for now, let's make some definitions. Let's make a definition. Let x and y be two spaces. So in this class, we will just say spaces, and it will be understood that these are topological spaces. If you do not know what a topological space is, then assume those are metric spaces, if you're comfortable with that. And if you're not comfortable with that, then you can just assume that these are regions, these are subsets of Euclidean spaces. And that should be good enough for what we do. So let x and y be two spaces. We say two continuous maps. So f, let's say from x to y, and another map x to y. So these are two mappings from x to y, are homotopic if and only if there is a continuous map, let's call it H for homotopy. So x Cartesian product the interval 0, 1 into y. Now before we go on, before I say anything else, let's just understand some notation. So 0, 1, this is the interval, the closed interval from 0, 1. So this is a subset of the real line. If you're bothered by what this means, if you're unsure, like you might say, well, what does this mean? So in a topology course, you talk about these things called product spaces. So if you have two topological spaces, there's something called the product space. So you can take two spaces, you can put them into a product and turn that into a new topological space called the product space. If you're not sure what product spaces are, then what you can do is you can just go back to the Euclidean sense. So for example, let's just say that x is a subset of R2, okay, and x is the circle. This is the unit circle. How can you visualize x cross 0, 1, the Cartesian product? All this means is it's going to look like this. It's going to be a pair where the first coordinate, this is something in x, and the second coordinate, this is something in the interval from 0 to 1. Now, something in x will be a point. Let's call it x1 comma x2. So this would be a point, x1, x2. And something in 0, 1, this would be, let's say, a number. Let's call it t, where t is a number between 0 and 1. So if you maybe get rid of these extra brackets and you perhaps rewrite it in a nicer way, you would have x1, x2 comma t, where the condition is that the sum of squares has to add up to 1, and t ranges from 0 to 1. And if you can visualize what this is, then x cross 0, 1 is now a region in R3. It's in three-dimensional space because you've just added an additional coordinate. And how do you visualize this? Well, you have an extra axis that now goes, and then you would have your unit circle. This is unit circle, and then the additional axis ranges from 0 to 1. So we'll from 0 to 1, and then you get to see what you get. You get this cylinder. Okay, so this is like this is how you can think of this. So if you're not sure what the product space is, then you can always convert it back to the Euclidean sense, and then you're back to something that you're familiar with. So there's a continuous map. So you're going to take the product between x and the interval from 0 to 1, you're going to have this continuous map so that the following property is going to be satisfied. So h of x comma 0 is going to be f of x, and h x comma 1 is going to be g of x. So what's the idea here? So intuitively, so this is the intuition, intuitively, the homotopy map H, it continuously changes the function f into the function g. That's what's happening, right? You have two functions, f and g. So a homotopy between two continuous functions. By the way, map and function means the same thing. So a homotopy between two continuous maps is something that changes the first one into the second one. So when you take, you see, when you take, you can think of this as time, right? You can think of this perhaps as time. So at time 0, you get the original function, and at time 1, you get the second function. And as you vary time between 0 and 1, you're changing f continuously into g. So that is what we call a homotopy between two continuous maps. Okay, so now before we give any examples, I know you're probably wondering about examples. Before we give any examples, I want to make another definition, what it means for two spaces to be homotopic. Definition: let x and y be two topological spaces, or metric spaces, whatever you prefer. We say x comma y are homotopic spaces if and only if we can find two continuous maps. Let's call it f from x to y, and a map from y to x, so that if you do f compose g, that will, well, you see, with homeomorphisms, you want them to be the identity. So that f comma g, and this is the notation that we use, is homotopic to the identity on g, and g composed f is homotopic to the identity on x. So this symbol means homotopic to. Which is exactly this. So in this definition, you would say f, so the notation that we use here is we say f is homotopic with g. And it's an easy exercise to show that if f is homotopic with g, then g is homotopic with f. So it's like an equivalence relation. That's not difficult to show. That's like a good practice problem. So as you can see, in the definition of being homotopic, it's a little bit more general than being homeomorphic. If it's homeomorphic, then these are actually equal to the identity. But when they're homotopic spaces, then you're saying that there is a continuous way to transform this function into the identity, and a continuous way to transform the other composition into the other identity. And now let's look at some examples where we get to do this. So the first example that I want to start with, and this is a nice example, so let's start with this example. So let x denote the complex numbers missing the origin. So this is what we call the punctured plane. And as a set, this would be the set of complex numbers where z is not equal to 0. You can also say that this is the complex numbers take away the number 0. Now the complex numbers have a metric. So if you want to understand what the metric here is, so given two complex numbers, so if you're given z and w, and these are complex numbers, you can write z as a plus ib and w as c plus id. Then the distance between z and w can be calculated by taking their difference and then taking the absolute value, the norm of that. So that would just be the square root of, you subtract off the real components, you subtract off the imaginary components, and then you take the sum of squares. So that's the metric on the punctured plane, which is basically the exact same metric as an R2. Right? It's almost the same thing. So this is a punctured plane, and like I said, this is a topological space. You could put a topology here, but if that bothers you, if you're not sure how to do it, then you can just use metric, right? You can just use the following metric, that for any two complex numbers, that's the way you calculate their distance. And here we're just avoiding these from being 0, so that would be x. And then y would be S1. So this is what we call the unit circle. Usually, the way we write the unit circle is we're going to use complex notation. We say that these are complex numbers whose absolute value is equal to exactly 1. You can also write the unit circle in real notation as a subset of R2, but this is going to be more convenient. So that's going to be S1. By the way, S1, because this is supposed to mean this is the one-dimensional sphere. But the sphere of one dimension. So S2 would be the usual sphere that you think about, and so on. We typically talk about Sn, the n-dimensional sphere. And what we're going to show is we will show that x and y are homotopic spaces. Now, if you look at the picture for x, so x is the punctured plane. So x is this entire plane with a hole missing. So maybe what I should do is, maybe I should just make a little point over here. So that's the punctured plane. See the punctured plane. This is x. And y is just the unit circle. Now, by looking at these two spaces, so maybe we should fill this one in. Maybe what we should do is, maybe the blue point, that's the center, and it's missing, but everything else is included. So that's the punctured plane, and this is y, it's just a circle. Now you can see intuitively that these are very, very different spaces, very different. That no matter how much you twist this one, you can never make it fill all of that out. I mean, you would even say that this is like a one-dimensional object because it's like a curve, and that's a plane missing just one point. So it's like in some sense, it's like a two-dimensional object. So how can you possibly transform one into the other? And it could be shown that x and y are not homeomorphic. So it could be shown that x and y are not homeomorphic. The easiest way to show this, so here you have to be familiar with some point set topology. I think the easiest way to see this is y is a compact space and x is not a compact space. So y has a property that x does not have, so they cannot be the same topological space. But in this exercise, we want to show that they're homeomorphic nonetheless. Before we do anything, let's draw a picture for what we're about to do. So in x, we can find the circle, right? We can draw the circle in x. So let's go ahead and draw the unit circle in x. So that's the unit circle. And what we will do next is, what's the idea behind a homotopy? The idea of a homotopy is the two spaces could be different, but one space can be converted into a different space through a continuous process. You can continuously change one space into another. So the way this would work is you will start at the center. This is going to be the idea. You're going to start at the center, and you're going to push everything out to the boundary. So if you take all of the points inside that disk, you can push them out to the boundary. This is actually the reason why it's important that the origin is not part of the space. Because if the origin was part of the space, that would be a discontinuous operation, right? Because then where does the origin itself go? Where exactly do you map the origin? No matter where you map it, the points nearby will get mapped to the other side. So that would not be a continuous process. But this is sort of a continuous process where you're gradually just pushing everything out to the boundary. And on the outside, you push everything out to the boundary like this. And then you end up with the boundary circle. So you can convert the punctured plane in a continuous way to the circle. Now let's do this in a rigorous way. So we need to find two continuous maps, f from x to y and g from y to x, so that if you do, let's say, g composed f, that would be homotopic to the identity on x. And if you do f composed g, that would be homotopic to the identity map on y. So let's see how to do this. Now observe that y happens to be a subset of x, because the unit circle is part of the punctured plane. So let us map y into x by the inclusion mapping, by the formula that the complex number just goes to itself. This is called the inclusion mapping. This makes sense, right? Every complex number is being mapped to itself because it's already, y is already contained in x. Now, how do we go the other way around? So now define a map that goes from x to y as follows. So you have to say what it does to a complex number. So you pick something in x, and you have to produce something on the unit circle. So here's what you need to understand. Whatever this x is the punctured plane. So z is a non-zero number. Because it's non-zero, that should indicate you probably want to divide by it. Okay? And the way you do this is you're going to do z, and you're going to divide out by the norm of z, the absolute value of z. So this will renormalize the complex number, and it will give you a complex number that has norm 1. So that would now be on the circle. And that's basically what this picture is doing. So going back to this picture, if you have the complex plane, and this is the missing origin, if you have some complex number and you draw like this vector z, if you divide z by its norm, then you end up on the unit circle. So that's basically what you're doing. So we've just constructed two functions, and we claim that f and g are what are known as homotopy inverses. They're not inverses because the spaces are not homeomorphic, but they're homotopic to the identities. So they're inverses in the homotopy sense, that these compositions will give you the identities. So one of these is easy to check. So let's start with f composed g. So f composed g would be a map from y to y, right? Because g is a mapping from y to x, and f is a mapping from x to y. So this composition is a mapping from y to y. And if you calculate what it does to a point in y, so if you pick something in y, g of y is just itself, because g is the inclusion map, as we've said, and f of z is the renormalization function. But because z is already on the, you see the z is already on the unit circle, its norm is 1. So this is just z divided by 1, which is z. So f composed g, this is actually equal to the identity on y. That's just the identity mapping on y. So you do not even have to show it's homotopic to the identity. It happens to be equal to the identity. So that's even better. But now let's do it in the other direction. So now let's work with G composed F. So this will be a map from X to X. So let's work out what the formula here is. So if you do G of F of Z, what is that equal to? So this would be G of F of Z. So F of Z is Z over the norm of Z. Okay, Z over the norm, because that's what F is doing. F is the function that renormalizes the complex number. So G of this. But because Z divided by its norm, that's on the unit circle, G is the inclusion mapping, so that's just equal to itself. Okay, so that's what this is. So and the identity map on X. So the identity map on X is given by just Z. So we have to find a way to, so we have two functions. Notice that in this case, G composed F is not equal to the identity map. But what do we want to do? So to show that G composed F is homotopic to the identity on X, we need to find a continuous map H, X cross 0, 1, into X, so that so I know that, let me just take it back a little bit. I know that in the definition previously, it went like this, right? This is the way the previous definition went. Because in that definition, we're trying to show that F is homotopic with G. F is a map from X to Y, and G is a map from X to Y. But here, we're trying to show that this composition is the identity. The composition is a mapping from X to itself. That's why there is no Y here. It's X and X on both sides. And the identity is a mapping from X to X. So that's the reason why it's being set up in this way. So we need to find a homotopy map so that if you do H of Z comma, let's say, so time between 0 and 1, let's say at 0, you get the first map. This is the first map, G composed F, which is the map Z over its norm. And at Z is equal to 1, you get the other map, which is just Z. So you want to find a way to change this function into this function in a continuous way. So let's call a real number between 0 and 1. Let's call it by the variable s. And this is Z. So this is a complex number in the punctured plane. And this is S. This is a real number between 0 and 1. So let's construct H. So we need a general map, H, Z, comma, S, a continuous map that will give us something in the punctured plane. And when S is equal to 0, it will give us that. And when S is equal to 1, it will give us this. So this is like a common trick that is often used. Sometimes it works, sometimes it does not. But in this case, it works fine. You're going to write it like, you're going to write it as Z over the norm of Z. And let's put over here 1 minus S. And here we're going to write S times Z. So notice what's happening. When S is set equal to 0, this drops out. And you're left with 1 Z over the norm of Z. You get this one. If you set S is equal to 1, then this becomes 0. So this drops out, and you're left with just Z. So it satisfies the requirements that between 0 and 1, it continuously moves this function to that function. So what do you need to check? So we only need to check that H is continuous and H is a mapping from that product into X. So we're going to skip the part where you check that it's continuous. Generally speaking, when you combine continuous functions together with like a sum or a product or something like that, it's going to give you a continuous function, right? This is like a common theme you've seen in like advanced calculus, that if you have continuous functions and you add them together, then there's no issue. it's true you are dividing by the norm of z, but you need to understand that x represents all complex numbers which are non-zero. So you are dividing by something that never vanishes, and so it's a continuous mapping. So this is a continuous mapping. There's no issue here. This is just some general fact about continuous mappings, that if you combine them, you get something that's continuous again. So we're going to skip this part. This is the one that's a bit more important because you actually have to show that this is the domain, and that's the codomain. You have to show that the codomain is included in X, because the only thing we know about this is that this is a complex number. But the requirement of a homotopy is that it has to map X to X, not X to the complex plane, right? We're trying to establish a homotopy between this composition and the identity on X. The identity is a mapping from X to itself. It's not a mapping from X into the complex plane. So you cannot put, you have to have the same X here. So the codomain has to be X. The only thing we know about this quantity is that this quantity is in a complex number. So at the moment, we know that this is in the complex plane, but we want to show that this is actually in the punctured plane. So in other words, this is non-zero. And you can check this very easily. So it is easy to show that 1 minus sz over plus sz is not equal to 0. So it's in the punctured plane. So how do you show that? Well, I think what you can do is you can divide both sides by z, and you're allowed to divide by z because z is a non-zero number. So you can divide out by it. And then we're left with 1 minus s over the norm of z plus s is equal to 0. Okay, now if we move them over to the other side, we have 1 minus s over that is equal to negative s. And now you notice what the problem is. This number is negative, and this number is positive. Though one has to be a little bit careful, because what if s is 0? If s is 0, then this number is 0, this is 1, and that's positive. So this would be positive. That gives you, so this is impossible. Otherwise, s is a positive number. Keep in mind, s is between 0 and 1. So then s is a positive number. So then this is positive, and then 1 minus s, that's also going to be, yeah, so this is the negative, and this is going to be positive, 1 minus s, unless, of course, s is 1. But if s is 1, then this is 0. So this is impossible. Like, basically what happens, one of these is positive, one of these is negative, and that's why this is an impossible result. And so basically, this is a valid homotopy. It converts the first mapping into the second mapping, the identity mapping, in a continuous way, and we have therefore shown that two spaces are indeed homotopic spaces. Now, this trick that we did over here, it can be, it comes up a lot when you're working with convex sets. So let's say what a convex set is. Okay, so let's make a definition here. We say that X as a subset of Rn, and here you will notice I am emphasizing that X is a subset of Rn because what we're about to write down would not make sense in general. This is not a topological notion. It only makes sense in Euclidean spaces. So we say that X in Rn is a convex set if and only if for any 2 points P and Q in X, we have that the interval from P to Q is contained in X, where P and Q, the interval from P and Q, this is the line segment between P and Q. You can describe this as the set of points S, P. Actually, let me write it like this. 1 minus SP plus SQ, where S varies between 0 and 1. Okay, so just so we understand, P and Q, these are vectors in Rn. So these are P and Q, they belong to X, but X is a subset of Rn. So these are vectors in Rn. And these these are scalars. These are just real numbers. And you are multiplying a scalar by a vector, and then you're adding them together. This is then vector addition. This is the reason why this does not make sense in a topological space. In a topological space, you cannot add points together, and you cannot rescale them by real numbers. That would make no sense at all. So the picture here is, so here's the picture. The picture is that X looks something like this, that if you have point P and you have point Q, then this is the interval from P to Q. Because when S is equal to 0, you pick up P. When S is equal to 1, you pick up Q, and that becomes 0. And when S ranges from 0 to 1, that's everything that's in between P and Q. So you get a straight line segment because this is like a degree 1 expression. So you're going to get a line segment out of that. So convex means for any 2 points in X, the line segment that connects them is part of the set. An example of something that is not convex would be something like this. Notice in this case, if you have P and you have Q, then if you were to draw the line segment between them, notice the line segment between them falls outside the set. So this is what we call convex, and this is not convex. And the nice thing about convex spaces is the following. So we've given the definition of what it means to be convex, and now let's give an example. So here's another example. So suppose X, so X, this is some subset of Rn, is convex, and P, it's called P is just any point in X, so a non-empty convex set. Then X is homotopic to just a single point. So let's draw a picture, maybe to make this believable. So here's like a picture of something that's convex. And what we're saying is if you pick a point in X, then there's like a continuous process that can be used to bring everything down to the point. So this is like an extreme case of homotopy. X is some absolutely enormous uncountable space. It has an uncountable number of points, usually. And it's homotopic to just a single point. It's just that point. It does not matter where you pick the point. It's homotopic to a single point. So how do you prove this? Well, we need to construct a function from X to the point and another function from the single point to X, so that if you do F compose G, that will be the identity on the single point space, and if you do G composed F, that would be the identity mapping on X. I'm sorry, let me take it back. It would be homotopic to this and homotopic to that. Now, they're not going to be equal. There's no way that X is going to be homeomorphic to a point unless X is a point itself, because X is an uncountable space. There's no bijection, just on the set theoretic level, just ignoring continuity. There's no bijection between X and that point. But nonetheless, they will be homotopic spaces, because you can see from the picture, you can continuously move everything down to a point. So let's work this out. This is not difficult to show. So we need to construct our two functions. So for the first function, well, because it's just a single point, there's only one way to do it. If you pick something, let's call it lowercase x. So if you pick something in this set, so if you have a vector in that set, it has to be mapped to P. There's nothing else you can do. And the other one, G of P, well, where do you want to map this point, right? There's only one point, and it could be mapped anywhere, right? That's automatically going to be a continuous map because it's just a map on a single point. Where do you want to map the point? Well, it does not matter where you map it to, but maybe for convenience, you just map it to P itself. Okay, so the picture here is, here's X, here's a point P, here's a single point P. This is the single point, the set that contains the single point. And the mapping is, the mapping F collapses all of X down to this point P, and the mapping from P into X just maps the point to where it is in X. So this is like the inclusion map, right? This is actually the inclusion map. Actually, it does not need to map it to X. It could map it anywhere else, but it does not really matter. And now we have to check these conditions. So if let's do F compose G. So if you do F of G, so if you do this composition, well, G is only evaluated at P at nowhere else. So this is going to be F of P, and F of P is just P. So F compose G, this is actually equal to the identity mapping on the single point space. The other way, well, let's do it the other way around. If you do it the other way around, really we should call that X. F of G of X, this is the other way around. Well, F of X goes to P, so this is G of P, and G of P is P again. Okay, so this condition is true. So this is fine. It's not just homotopic to the identity, it's equal to the identity. So this is the one that we have to check. So we have two mappings. So G composed F at X maps everything to P, and the identity on X evaluated at X gives you X. So we need to construct a homotopy map. Let's call it H, from X cross 0, 1 into X, so that at time 0 you get this mapping, the constant mapping P, and at time 1 you get the other mapping, which is the mapping X. And it's similar to what we did in the previous exercise. So the mapping function X comma S, notice it's a product, so it's something in this set and some number between 0 and 1. The way we're going to do it is we're going to do, let's say, 1 minus S times P plus S times X. Now here's where it's important. So this is the part which is very important. So in general, this is in Rn, because these are vectors, P and X are vectors in Rn, and you're just rescaling them by these two numbers and you're adding them together. But since X is convex and P and X, lowercase x, belong to this convex set, we know that the line segment between P and X is included in this convex set. And the line segment is parametrized by all of these as you vary S from 0 and 1. So all of these are in the line segment, and the line segment is contained in X. So the important point here is when you're constructing the homotopy map, it has to go from X to X, not from X to Rn. It has to actually go from X to X itself. So this is why we know that you can just put an X over there. And now it's easy to check what happens when, and again, as before, it's believable that this is a continuous map because you're adding two things together. This is the identity map, this is a constant map, you're adding them together, you're rescaling them, so the function you get out of that will be a continuous function. And you can see what happens as S varies from 0 to 1. If S is equal to 0, then X comma 0, this would be, so if you set S is equal to 0, you get P. And if you set S is equal to 1, then you get X. So you've established a continuous way of transforming the constant function into the identity function, right? So these are the two functions you have to transform in a continuous way. So if you've just proven that convex sets are homotopic to a single point, okay? So for example, for instance, let B3, this is the solid three-dimensional unit ball. Let's say closed unit ball. So if you want to write it out, you would say it like this: x1, x2, x3 in R3, with the condition that the sum of squares not only is it equal to 1, but it's less than or equal to 1. So this is the solid three-dimensional unit ball. So it's like a ball, and it's completely solid inside. So then the three-dimensional unit ball is homotopic to its center. Right, this is an enormously large set, uncountable set, and that's just a finite set with one number in it. So they're homotopic, and right, like that's the very center. And the reason why it works is because you can just bring everything in. Now, however, it will be shown later that S2, this is the two-dimensional sphere, is not homotopic to its center. So this is the two-dimensional sphere. So the two-dimensional sphere would be that, but not including the stuff in the middle. You see, here we're writing B3 because by including the stuff in the middle, you're getting like a three-dimensional object. Whereas S2, that's just the surface of it. That's a two-dimensional, because if you cut a sphere open, you can kind of make it flat, so it's two-dimensional. But that's the solid ball. That's why we write this as B3 and this is as S2. We're not, you see, you have to understand, even though when we draw the two-dimensional sphere, we're drawing the two-dimensional sphere in three-dimensional space, but the two-dimensional sphere as an object in and of itself is a two-dimensional object. That's why we write S2. So the two-dimensional sphere is not homotopic to that. Now, also, right, I mean, you can see S2 is not convex. Of course it's not convex, because if you pick 2 points on the unit sphere and you draw the line between them, the line will pass through the middle of the two-dimensional sphere, and that's not part of the two-dimensional sphere. It's not convex, right? It's not easy to prove this. Well, I mean, showing it's not convex, that's easy. What I mean to show is that S2 is not homotopic to its center. That's not easy to show. I mean, intuitively, it makes sense, right? Intuitively, I guess it makes sense because you have all that empty space inside. You see, you're not allowed to do this. If you're wondering, like, what would be the problem with just gradually moving everything down to the center and making the sphere smaller and smaller, you can say this. You start with a sphere like this, then you make the sphere a little bit smaller, then you make the sphere a little bit smaller, then you make a sphere a little smaller, and then you keep on doing it until you get a point, and then, which is the center, and then you have continuously transformed the sphere down to a point. So what would be the problem with that? Well, the problem here is that it goes back to what we were saying. When you construct the homotopy maps, it has to be a homotopy from the same space to itself. It has to go into itself. And these smaller spheres, they're not part of this sphere. These smaller spheres, they're part of the three-dimensional ball because they're included inside of it, but they're not part of the two-dimensional sphere because it's hollow inside. So these smaller and smaller spheres, they're not part of the two-dimensional sphere, right? You're sort of escaping outside your space. And with homotopies, you have to stay within your space. So that's why you're not allowed to do that. So it will be shown later why the sphere is not homotopic to a single point. That's actually not easy to show. Intuitively, I guess you can say it makes sense. You cannot collapse a sphere down to a point because it's empty inside. It makes sense, but proving it rigorously, that's harder to do. So that would be an example. Convex sets are examples of many examples all at once. Let's move on to another example, which is a lot more challenging. Now, the two previous examples had the inclusion map. So what we had was, we had X and Y. Those were the two spaces, and X was a subset of Y. And then what we had was that one of the mappings was the inclusion mapping. And so when you do G composed F, then this was actually equal to the identity on X as opposed to being homotopic to the identity map. So you might get this wrong impression that whenever you're doing these kinds of homotopy problems, that you need an inclusion and you need one of the compositions to equal to the identity map. And this is not the case. So this next example will be a little bit more challenging, but I think it is a nice example, and it shows that you do not necessarily need to have inclusion mappings. One does not need to be a subspace of the other. So here's going to be our space X. So imagine, so maybe we'll do it like this. So this is not part of the space. This is just a way to help see what's going on. So this is going to be our space. We're going to have a circle of radius 1 and another circle of radius 1. So this is going to be X. And Y is going to be a circle of radius 1. And then we're going to include this diameter as well. So that's going to be Y. So Y together with the line. So X, this is called a figure 8 space for obvious reasons. And this one is called the theta space, also for obvious reasons. The notation that we use for X is we sometimes write S1 V S1. The V is supposed to represent a one-point union. So these are two circles joined at just a single point. But that's just notation. So this is X, this is Y. And we want to show, we're going to show X and Y are homotopic spaces. And the way you can perhaps convince yourself on an intuitive level that these are homotopic spaces, if you look at this diameter, this entire diameter, well, it's, as we've said before, it's convex, right? The diameter is convex. So this entire diameter can be continuously shrunk down to a point. So you can shrink the diameter down to a point. And now notice what happens, that this, as you shrink it down to the point, the two points at the extremes on the diameter, as you shrink it down to a point, they come together. And as they come together, you get these two circles over here. So that is sort of the intuitive justification for why X and Y are homotopic spaces. Now, if you want to be a little bit more rigorous, then you actually have to work and produce the mappings that do it for you. So let's discuss how this would go. Maybe what I'll do is I'm going to redraw these pictures without the axes. So we have the figure 8 space, and then we have our theta space. And let's describe the first mapping. So this is what F is going to be doing. So maybe it would be helpful to introduce these lines right over here. And we're going to describe, so this is going to be X, this is going to be Y. So let's describe what the function F is doing. This is F. So what F is going to be doing, you can write out the formulas for this, of course, but let's describe it visually, and then at the end of the problem, we'll write out the equations for these maps. But visually, what this function is going to be doing is it's going to take this upper cap. So you have this upper cap over here. And this upper cap is going to move it down to this upper cap. So you just take this upper cap and you slide it down. So this is a circle of radius 1. This is the origin. This is the origin right over here. So if you take this cap and you slide it down, you get this upper cap. And the same thing with the lower cap. This lower cap over here will go to this lower cap. And then you have this piece in the middle. This is what we call the chromosome. So this entire chromosome, what you're going to do with the chromosome is you're going to project it to the diameter. So what we're saying is you're just going to project it. You're just going to like vertically push it down. So as you vertically push it down, you get this diameter. So this is what the function is doing. You can, of course, write out the formula for this, but I think it's more helpful to just visually describe it. And you should check continuity. The point which is a bit suspicious is right on the barrier between the blue and the red. So this point right over here, if you're using the red definition, then this point ends up being right over there. If you're using the blue definition, then by projecting it down, it ends up right over there. So the function is continuous. So that's a continuous mapping. And now we want to describe the function going in the other direction. We now need a function from y. So this is going to, let's call this one G. So now we have to, so when we're doing homotopy equivalence, we have to find the function from x to y, and then we need to find the function from y to x. That is the homotopic inverse. So when you compose the two mappings, they're homotopic to the identity mappings. So here we have to go back to the figure 8 space. So let's describe what happens here. So with this mapping, the entire diameter, this blue diameter, it's going to get shrunk down to a single point. So you're going to shrink, so this entire diameter goes down to a single point. Now you have the upper cap and the lower cap. Well, the upper cap, so this is what's going to happen with the upper cap. The upper cap gets wrapped around by a factor of 2. So let me explain that part a bit more carefully. So if you look at this unit circle, this is like a half circumference, whereas this is the full circumference. So when you wrap it around, its length gets multiplied by a factor of 2. So you're sort of just taking this, and you're, like, what I'm saying is, if you just take this upper cap, you make it twice as long, right? You just like make it twice as long, and after you make it twice as long, you can then wrap it around the circle. So that's basically what you're doing. If that's a bit unclear, maybe to make this a little bit easier to understand, this topmost point goes to the topmost point. Now, if you have a point over here, it produces a certain angle, theta, okay? And the angle will get doubled. So you're going to double your angle. This will become 2 theta. You will double the angle. So when you go from 0 to pi, because this is a half circle, when you double the angle, you go to the full circle. You go from 0 to pi here, and then from 0 to negative pi there. I'm sorry, theta goes from 0 to pi over 2, but here it goes from 0 to pi and 0 to negative pi, depending on whether you're on the right or left side. So that's basically what you're doing. You're just doubling the angle, and that's the way the mapping is achieved. So you can, of course, write out a formula for that, but we'll do that afterwards. We're actually going to write a formula for the homotopy map in the end, and that will give you the formula for it. So we have these mappings, and let us prove, so let us show that F and G are homotopy inverses. So here's what we'll do. So we will only show that if you do, so in this picture, we're going to do F first, and then we're going to follow through by G. So we're going to show that G composed F is going to be homotopic to the identity map on X, and you will show the other one. You will show, this is a homework problem, you will show that when you do F composed G, then this is going to be homotopic on Y, to save time, because this is a more involved exercise in homotopy. It's a more interesting example in homotopy, because you see, it's a little bit different from the other two examples. The other two examples, one of the mappings was the inclusion mapping, and so what ended up happening was one of the compositions was already the identity, so you do not have to do that much. But this one is a bit more challenging, but I think it's a nice example. So we're going to do this one together, and we'll carefully write out the homotopy map, and then you'll do the other one. I'm not sure if the other one is easier or not, but you'll do the other one. I think the one we're doing is harder, so you'll do the easier one. So we'll show this one. So let's figure out this composition where we do F composed G. So let's write out what the composition is doing in this map. So if you do the composition, you can see that this figure, it goes to the diameter. The blue figure goes to the diameter, and then the diameter goes down to a point. So really the composition, when you go from X to X, so this is X again, this is really what the composition is doing. So let's just remove all of this. Let's just say what the final map is. So this is X. And so what the composition is doing is you're going to have your figure 8 space. And the blue piece goes down to that point, whereas the red piece, it gets wrapped around the upper circle, and the lower cap gets wrapped around by a factor of 2 around the lower circle. So this mapping over here is what we're calling G composed F. So maybe to see this a little bit better, this chromosome, it gets collapsed down to a point. So we'll indicate this by saying it gets multiplied by 0. So if you multiply any of these points by the 0 vector, so 0 here means the 0 vector, or I'm sorry, not the number 0. If you take any one of these coordinates, you multiply by 0, you get the origin, so you end up at the origin. Whereas this upper cap, it's being expanded by a factor of 2. Now, it's not as simple as just multiplying it by the number 2. Of course, if you just take any one of these points and you multiply it by the number 2, you just expand it further out. But the 2 here is just supposed to represent that it's the map. We have to find the equation of the map, but it's the map that will sort of like expand the length of the arc by a factor of 2. That's what the 2 is supposed to represent. And this one is doing the same thing with the lower piece. It expands it by a factor of 2. And now let's describe what the identity map is doing to the same picture. So you have your figure 8 space over here. And let's draw the figure 8 space again. And here we're going to have the identity map on the space X. So what would happen this time is that, so this time what would happen is this entire chromosome-shaped piece, when it's the identity mapping is not going to do anything, so it would just be itself. So we'll stay exactly as it is. So we indicate that we multiply this by 1, so we're not doing anything. And then the upper cap under the identity mapping will go to the upper cap. So this one gets multiplied by a factor of 1, so it's not being expanded. And this lower cap goes to the lower cap under the identity map, and it gets multiplied also by a factor of 1. So this is the identity mapping. That's what the identity does. And a homotopy is, we have to construct a homotopy that will continuously transform this into something like this. Okay, so what are we trying to do? So we want to find a homotopy map. Homotopy map. Let's call it H. X cross the interval 0, 1 into X. I'm sorry, into X. So that if you do H of, now a point in X, it's just because X is in the plane, it's a pair of real numbers. So let's call it X comma Y, like this, lowercase x comma Y. That if you set time equal to 0, you get this mapping, G composed F. G composed F at X comma Y. And if you do H of X comma Y at 1, you get the identity mapping, which just means you just get X comma Y back. The point goes to itself. And maybe you can see visually what's happening. So at time 0, the blue piece gets multiplied by 0. It collapses down to a point. And at time 1, both of the caps are rather multiplied by 1. They're not being expanded, and the chromosome is also multiplied by 1, so it's not changing. But what happens to all of the intermediate moments in time between 0 and 1? So maybe what should happen is that at, let's say, H, X, Y, let's say at a half, should look like, so if you choose some intermediate moment in time, then the mapping should be the intermediate mapping. So this should be the mapping that will do this. It will take the figure 8 and we'll map it to the figure 8 according to the following rule. So it's going to do it in this way. So as before, we just draw these in for the sake of illustration. But then the idea would be that this entire chromosome that you have over here, instead of being multiplied by 0, it gets multiplied by 1/2. So it becomes like half as big as it was. See, it becomes half as big as it was. And then the two caps, the upper cap and the lower cap that you have over here, this cap will get multiplied by 3 over 2, and this one gets multiplied by 3 over 2. So it gets a little bit further extended beyond that line. That's what's going on. And this is the way you can visualize the homotopy. That basically what's going on is the blue one is shrinking down to 0, and the red one is expanding out by a factor of 2. So at the two extreme cases, so if the time parameter, we call that s, if s is 0, then we get this one. If s is 1, then we get that one. And if s is any number between 0 and 1, we get some intermediate process. So if, let's say, s is a half, then we have something like this. And then you can maybe perhaps begin to visualize what the homotopy is doing. So this is like a nice example that nicely shows how homotopies work. But let's actually write out the equations for this, just for the sake of practice. So let us determine this function h x comma y at s. What is it equal to? So that's what it's doing visually as a picture, but maybe for the sake of practice, it would be helpful to draw what's going on. And to figure out what this is, you can consider 4 separate regions. So we can have 4 separate regions that make this up. So you have the upper cap, then you have the lower hemisphere, but the positive side. You have the upper hemisphere, but the negative side, and then you have the lower cap. So there's like 4 separate regions. Let's look at the topmost region first. So with the topmost region, so we have this. Let's just look at this upper cap over here. The way we determine what's happening is if you pick a point, let's say x comma y, there's a certain angle, theta, that's being produced. And when you map it using that picture that we drew, here's where it's going to end up at. You're going to multiply it. Now, you're going to multiply it by s, right? That's the idea. Well, actually, let's try to figure out how this gets multiplied first. Notice that this one is supposed to be multiplied by 0, and then it gets multiplied by 1. So the reasonable letter to use is just s. So if s represents some number from 0 to 1, notice when s is 0, this is where this thing gets multiplied by 0. And then when s is equal to 1, then it gets multiplied by 1. So it makes sense why we're going to use the letter s for this portion. Now for the upper portion, it gets multiplied by 2. So then the correct way to write it over here would be 2 minus s. 2 minus s, because when s is 0, this is 2, and when s is 1, this is 2 minus 1, so that will become 1. So we therefore are going to be multiplying it by 2 minus s. So if this angle is theta, based on the way this homotopy map works, is that in general, this upper cap will get expanded by a factor of what we said, 2 minus s. So that's how the angle will get expanded by. So if the angle over here is theta, then the expansion factor, it would end up somewhere over here, x prime, y prime. And by the way, it is conceivable, of course, that it goes all the way down here. That's fine. It could go further down. It's just, I do not want to draw that picture. I think this is simple enough to illustrate. So this would be 2 minus s times theta. So let's determine what x and y are in terms of theta. So x would be, here you have to be a little bit careful, this would be sine theta, and y would be cosine theta. This would be cosine theta because the angle is measured from this axis, right? So sine, that would be opposite. X would be sine of this, whatever this angle is, and y will be cosine. So if you're on that side, it's positive angle. If you're on the other side, it's the negative angle. And technically with y, it's not cosine of theta. Everything is being moved up by 1. So it's really cosine theta plus 1. Because keep in mind, the y coordinate is moved up by 1. So that would be y. And here you have the same thing. The new coordinates for x, this would be sine 2s theta. And y prime would be cosine of 2 minus s times theta. And of course, it gets, you have to add in 1 over here because everything's moved up by 1. Okay, so that's the way you get these formula for the new coordinates for y prime. Now you have to express everything in terms of the original x and y, and you do that by solving for theta. So it's going to be more convenient to use the first equation. So let's get rid of this. So let's solve for theta. So this means that theta would be equal to the arc sine of x. And that's good because arc sine always returns for you an angle between minus pi over 2 and pi over 2, which is exactly what we want. We want theta to vary between minus pi over 2 and pi over 2. If we rather solved for theta using arc cosine, we would have a certain problem because then that would mean that y will not necessarily fall into the correct range. So every time you're using these inverse trigonometric functions, you have to pay very close attention to the range that you're located in. But when you're using arc sine with x, then it works out just right. So then the angle will correctly vary from negative pi over 2 to pi over 2. So that's what theta is. And then you can from here figure out the coordinates for what the map is doing. So that means that x prime, the new coordinate on x, would be sine of 2 minus s arc sine of the original x, and y prime would be cosine of 2 minus s arc sine of x plus 1. So that's what this would do. It feels like you should be able to simplify because you have sine and arc sine, but this is an annoyance factor, so we just have to leave it the way that it is. There is no identity where you can apply sine to an arbitrary real number. If this is like 1, then you can simplify. If this is 2 or 3, you can simplify like one of those double angles, triple angles. But in general, if this is some irrational number, there is no identity to take out an irrational angle, an irrational multiple out of the sine of an angle. So you just have to leave it the way that it is. So that's the way you find the new position. So, and then the same thing's going to happen with the lower portion. So with the lower portion, you're going to have the exact same kind of equations that we just described what this homotopy is doing on the upper piece, and now you can describe what it's doing on the lower piece. So on the lower piece, if this is your lower piece, like this, and you have a point xy, this is the lower cap, and you have a certain angle theta, then for the same reasoning as before, you're going to get new coordinates x prime, y prime, and the angle gets multiplied by a factor of 2 minus s theta, and then you can find what x prime is and y prime is. So I'll just write it out because it's almost the same thing. So this is going to be sine 2 minus s arc sine of x. So there is no change on x. That makes sense. And the difference that happens with the y prime is that if you carefully think about this, you're going to have to use a negative because it's going down. You have to use negative cosine arc sine of x. And then instead of adding 1, you have to subtract 1 because it goes down. Okay, so that's the equation of the homotopy in the lower, for the lower cap. And now we have to figure out what the homotopy is doing on the intermediate pieces. So let's take this down. I'm going to put these back in again, and you'll see the final completed function in the very end. But now you have to describe what the homotopy is doing. So this is our figure 8 again. And we said we kind of break it up like this. And then we also break it up like this, just for the sake of convenience. So we've described what it's doing on the upper cap. We described what it's doing on the lower cap. And now we're going to focus what it's doing on this upper chromosome. So as we indicated that on this chromosome, on this one will get suppressed by a certain factor. So the multiplication factor is going to be s. So let me just quickly remind you, for the upper cast, the multiplication factor was 2 minus s. On the chromosome part, the multiplication factor is going to be s. So this one gets suppressed by a factor of s rather than being expanded. And of course, just to draw the picture again, this is our upper cap. The upper cap is the one that's being expanded by a factor of 2 minus s. But we already figured out the equation for the mapping for the upper cap. So now we want to focus on the upper chromosome. So we're going to draw the picture again. So here we're going to have this is going to be our circle like this, a piece of a circle. And the way this mapping works is that if you have a point, let's call it x comma y, and it makes a certain angle over here, theta, then this piece of the circle, it will get contracted by a factor of s, so it's now s theta. Remember, s is a number between 0 and 1, so the angle gets smaller, and this would be x prime, y prime. And let's figure out what x and y is. So from this picture, x would be sine theta, right? This is the opposite side, so that's sine theta, and y will be cosine theta. And in this picture, x prime would be sine of s theta, and y prime would be cosine. Well, actually, okay, this is incorrect because this is not a circle that's centered. Yeah, this is a circle that's not centered at the origin. So maybe I should not. I'm just going to write what x is. X will be sine of the angle. The location for y will be a little bit trickier because it's the x coordinate is on center. Like if you just look at where the center of the circle is located, the x coordinate is 0, so it is where it's supposed to be. But the y coordinate is not. So maybe I should not write this out. So I'll just write x is equal to sine of the angle. And for this one, y prime, the correct way you find y prime coordinate in the picture, you're going down. You're going down on the circle. So it's going to be negative. So it's negative cosine. You multiply it by s. So it's s theta. And then you're going to add 1 because you're moving it up, right? So, of course, the usual sine and cosine formulas, that's when the circle is perfectly on center. But this one's not on center, so you have to do a little bit of adjustment. It's negative because you're technically in the lower half of the circle, and it's +1 because everything's being shifted up by +1. So if you carefully think it through, this is the way you write it. And now you can write out the equation for x prime and y prime in terms of the original x. So this would be sine of s times theta, and theta is arc sine of x because you can solve for theta, so it's arc sine of x. And then y prime would be negative cosine times s arc sine of theta, but it's +1. So this is what we end up getting in the end when we do this. And then we're going to have a similar situation for this for the upper chromosome of the lower half. But maybe what we can do is we can now summarize what the map is doing. So let me take all of this down, and then all of these equations, let's actually summarize what the function is doing. Okay, so to summarize, we have a map from the figure 8 cross 0, 1, and it's going to be defined as follows. So h x comma y comma s would be equal to, so this one will have 4 piecewise conditions depending on where you're located on the figure 8. So x comma y, that's just referring to a point on the figure 8. So if you're located in the topmost part, the formula, this is what we had before, this was sine of 2 minus s arc sine of x. That's the x coordinate, and the new y coordinate is cosine 2 minus s arc sine of x +1. And this is if y is at least 1. So if the y coordinate is at least 1, that means you're in this upper piece. And then this is the new x coordinate, that's the new y coordinate. Then the other one is going to be sine. This is s times theta, and theta is arc sine of x. And this is what we were saying, you have to use negative cosine s times theta, so that's arc sine of x +1. And this is if y is less than or equal to 1, but is greater than or equal to 0. So it's positive, but it's less than 1. So you're in this portion. So if the point is in this piece, then this is the way the homotopy map is being defined. And then let's jump to the last one. This is what happens if y is less than or equal to -1. You're in this lower piece. This is the one that we worked out also. This is the one which was sine 2 minus s times theta. So that's arc sine of x. And this is minus cosine 2 minus s arc sine of x minus 1. And this is if y is less than or equal to -1. And the only one that we really have to focus on is if y is negative but greater than or equal to -1. And it's basically exactly this, but the change will occur that in this upper piece, you are using the upper piece of the circle, so it's going to be positive, but this is going to be -1 because you have to slide it down by -1. So this is going to be sine s times theta. So here theta is arc sine of x. And this is going to be positive cosine of s arc sine of x minus 1. Okay, so this is the homotopy. It's pretty complicated. I mean, writing things out explicitly is complicated, but there's your homotopy. So you actually have to check. So you need to check that H is a continuous mapping. Here you actually have to make a small little check to verify that this is a valid continuous mapping. So the reason for this is because if you look at the functions that make up the mapping rules, they consist of sine, arc sine, and then adding 1, subtracting 1, multiplying by s, multiplying by 2 minus s. So none of these operations will make something discontinuous. The one problem occurs is on these overlaps. So on the overlapping regions, you have to check that as you transition from one formula to the next formula, that they nicely fit together in a continuous way. So that's like the one thing that you carefully have to check. And that's not difficult to do. Like, I'm just going to do the first two, so you just get to see what I mean. So you have to check what happens. What if y is equal to 1? If y is equal to 1, do both of these give you the exact same result? In other words, is it continuous? Does it continuously transition from one formula to the other formula? Like individually, they're all continuous, but when you glue them together into one complete map, is it continuous? Now, of course, it has to be based on our picture, but we still have to verify that. So what happens if y is equal to 1? Well, if y is equal to 1, then the value of x, you're all the way out here. Then x will be, so you're all the way out here. So then y is 1, and then x will either be 1 or minus 1, plus or minus 1, depending on which side you're located on. So you're either on that side or on that side. Let's say it's plus 1 for the sake of simplicity to illustrate something. So let's say it's plus 1. So if it's plus 1, then arc sine, this would be arc sine. So then x would be 1, and arc sine of x would then be pi over 2. Arc sine of 1 is pi over 2. And so what do we then have to check? Well, the upper formula would then be sine 2 minus s arc sine of, so that's pi over 2. That's the first coordinate. And the second coordinate is cosine 2 minus s pi over 2 plus 1. And the second function is going to give us sine s arc sine, which is pi over 2. And then this one is going to be negative cosine s pi over 2 plus 1. So we basically have to verify, are both of these equal? That's the question. Are they equal to each other? Because we're just checking whether these two functions, they agree on the overlap when y is 1. So basically we set y is equal to 1. We determine x has to be plus or minus 1. That tells us what arc sine is, and then we can figure out what happens. And they will be the same. It has to do with trigonometric identities. So if you just look at these two, you have sine of 2 minus s pi over 2. That would be sine 2 times pi over 2 is pi minus pi over 2 times s. And then it's one of those identities that's the same thing as s times pi over 2, because subtracting off the pi does not change sign. And this is exactly the same thing. And with cosine, it's something very similar, that you'll have cosine of 2 minus s pi over 2. So that would be cosine pi minus pi over 2 times s. But with cosine, when you take cosine of pi minus an angle, you get the negative sign. You get negative cosine pi over 2 times s. But that's exactly what we want, right? We're supposed to get negative cosine pi over 2 times s, and then you have that plus 1 plus 1. So you can see that they happen to agree with each other on these overlaps. And then you can check these two overlaps and those two overlaps. Everything nicely agrees with each other. And now that you have this function, I mean, this is a pretty complicated function, but if you're interested, you can actually get a nicer formula. If you want to do this, I mean, it's not really required to, but if you want to, you can get a nicer formula for G. You can get a simplified formula for, let's say, G composed F. So we described G composed F using a picture, but if you want to actually get the formula for the function, you just have to realize that this is what happens when you take the time parameter and you set it equal to 0. So you just have to set s is equal to 0, and that will give you what the composition is doing. So then you will get that you're basically just setting this equal to 0. So you will end up with, so if we just take this away, we would get that G of f of x comma y would be equal to, so you set s is equal to 0. So then here you would get that this is 2, this would be 2, this would be 0, this would be 0, this would be 0, this would be 0, this would be 2, this would be 2. And now you can go ahead and begin simplifying this. So this one would be sine of 0, that's 0, and this is negative cosine of 0, so that's negative 1 plus 1. So this entire piece is just going to be 0, right? So we can just replace this, all of this, by the origin. So this is just going to be 0 comma 0. And this one is also going to be 0 comma 0. That makes sense. We did say that the chromosome piece is supposed to go to the origin. And now you get to figure out what these are. So this is just an exercise in trigonometric identities. So in the upper piece, what do we have up here? Sine of 2 arc sine of x. So this would be sine 2 arc sine of x. So this would be, use the double angle formula. So that's 2 sine arc sine of x. And this would be cosine arc sine of x. So now you're just using, like you can see, now you're just using that sine of the double angle as 2 sine of the angle cosine of the angle. So this is sine of arc sine of x, so this is just going to be x. That's just going to be x. And cosine of arc sine, you have to use like Pythagorean identity, right? It's square root. Be like square root of 1 minus x squared. But I think this this simplifies. Yeah, I think this will simplify because if you're on the circle, you can simplify this even more, because basically what I'm saying is, if you're located, if you have a point on the circle, then because the circle is off center, the equation is x squared plus, what would that be, y minus 1 squared is equal to 1. So that would be y minus 1 squared is 1 minus x squared, or y minus 1 is equal to plus or minus the square root of 1 minus x squared. So this means that square root of 1 minus x squared would be plus or minus y minus 1. It just depends on which one you're located in. So here we're going to be using the positive root, so that would be y minus 1. So this would mean that this entire piece can then just be replaced by y minus 1. So that makes it look a lot nicer in the end. And so your formula is going to go like this. Instead of sine of all of that, you would just write over here 2x y minus 1. That would be your first coordinate. For this one, this is the lower piece, so this is going to be, I think, minus 2x y minus 1. And then you can do something similar for the other one. Like I'm not going to do that. I'm just kind of showing you how you can actually get some nicer simplified formula for the original maps once you have this homotopy.